We're VannaSwap, the ML-driven AMM to protect user liquidity. We love AMMs because it's decentralized and allows anyone to be a market maker. However, the unfortunate reality is that currently, many liquidity providers bleed money consistently through impermanent loss and lose money through LVR to arbitragers. LVR is an attempt to quantify the instantaneous loss that liquidity providers face when arbitragers trade against the pool. We can address this issue through dynamic fees. In volatile markets when LVR is higher, we can quote higher spreads and fees, which allows us to disincentivize arbitragers from making money by arbitraging against our LP liquidity. It also compensates liquidity providers for the elevated risk that they take. In call markets, we actually want to quote lower spreads and fees to incentivize user to come trade on our AMM so we can make money on their order flow instead of going elsewhere with lower spreads and fees. That's why we created VannaSwap. We're a decentralized AMM that allows anyone to be a liquidity provider, and we also have ML-driven dynamic and efficient quotes that allows us to quote spreads and fees like market makers efficiently to protect ourselves and our liquidity when there's elevated risk and volatility. To create VannaSwap's on-chain machine learning model, we first grab L2 order book data from Kraken. We build a linear regression model that's lasso regularized using sklearn, and then we convert it to Onyx runtime format, and finally upload it to IPFS for inference on-chain on the Vanna Blockchain.
So now let's dive into the structure and design of VannaSwap. The right-hand side is the pool manager where the liquidity providers and the traders interact. Thanks to the innovative Uniswap v4 technology, the trading fee that the LP collects can be dynamically decided by the hook contract by calling the getFee method. The hook contract decides its fee by receiving predictive volatility from the oracles. On the Vanna chain, the volatility oracle can leverage the power of native machine learning inference. It can get the data from the graph, quick node, as well as other sources and make prediction natively by the model saved on IPFS, just with a simple constant OP code. With cross-chain communication protocols like CCIP and Acceler, we can further support VannaSwap on any EVM-compatible chains. In this case, the volatility oracle will get its prediction from the cross-chain messages.
This is Jeffrey. So now I'm going to show you a quick demo of VannaSwap. So that we're in the landing page right now, and we click started. So we can see exactly the same model as Uniswap. You can select the token and swap. I'm going to select one ETH and swap for USDC. And if you click confirm, it's just like Uniswap. You successfully swap your token. It seems like really simple, but under the hood there's a lot of things happening. So first of all, the swapping fee of the LP receiving is actually determined by a hook. So let's dive into it. Here is our volatility oracle, and it has a magic function called setVolatility, and you can specify the model name and the input data, and then you can pass in this parameter to send to our dedicated blockchain, which is Vanna. And in the blockchain, it will use a machine learning inference call to compute the volatility and decide the fee of the AMM that you should charge. And then through this process, you can go back, you can pass into the hook to whenever they call this getFee functions and change the fee structure of the LP position. So if you click pool, you can actually see there is a LP pool created by us, and it shows the recent volatility as well as the fee get from our volatility oracle and the last update times. And also we have created a script that can automatically update the volatility, so you can always have the most up-to-date transaction fee. In addition to that, in order to that other blockchain can enjoy the on-chain machine learning inference code, the benefit of the on-chain machine learning inference code, we use Acceler and Chainlink CCIP to pass in the message whenever you set the volatility to other chain. So the hook contract in the other chain can actually receive the message from the Vanna and have the up-to-date volatility as well as transaction fee. So we have support the Acceler and Chainlink CCIP.
Lastly, we run a historical simulation of VannaSwap's dynamic fees versus a static fee constant product market maker, and we model arbitrage behavior for this historical simulation. In this example, you can see when the market crashes and when volatility increases, the on-chain machine learning model quotes higher spreads, The higher spreads reduces sharply the exploitable LVR on VannaSwap compared to the LVR on the static fee constant product market maker. With minimal LVR, this also leads to liquidity being protected because there's less exploitable LVR. And you can see from this red line here that we actually see a gradual increase in the difference of the balance of liquidity providers between VannaSwap and the constant product market maker.